This video will cover section 5.1. In section 5.1, we talked about scatterplots, correlation, and whether or not a least squares regression line should be fit to a scatterplot based on the appearance of our scatterplot. So in this video, I'll work on problems 3, 6, and 12 from section 5.1. And hopefully that'll give you a jump start on getting going with the rest of the homework problems. Problem 3 is going to be kind of difficult for us to talk about on the video because problem 3 involves looking at 6 residual plots. Or sorry, 6 scatter plots. I can put down a book here. This says 8.3, but it's problem 5.3 in our book. And you can follow along on your online book, and we can take a look at each one of these scatter plots. And it asks us for each of the 6 plots, identify the strength of the relationship, weak, moderate, or strong, and whether or not fitting a linear model would be reasonable. If we look at scatterplot A is a parabola. Now, in terms of the strength of the relationship, remember, that's how well the data follow a pattern. It doesn't have to be a linear pattern. It's just a pattern. This, I would say, is a strong relationship. That data is very well behaved and very close to, if we were to draw a parabola, that data would be tightly grouped around that parabola. So we would say that the data has there's a strong relationship. Now, would it be appropriate to fit a linear model? No, not at all, because this is clearly not linear. It's parabolic in shape. B is this example here. We would say that this is moderately strong in its strength. If you look at this data in this scatterplot B, if we drew a line through that scatterplot, that data would be very close to that line. We don't have a lot of extraneous points like we do over here in part C. So we would say here, I would say that's moderate. I could even get by with moderately strong. I wouldn't say strong. Strong, I would want it to be more tightly grouped, perhaps like in exercise E. This would certainly allow me to fit a line, though. I could fit a line to that quite reasonably. C, that's a hodgepodge of data, right? If we take a look at that scatter plot, that data is just sprinkled all over that rectangle. It doesn't appear to have a strong relationship. There is no pattern, be it a curved or a linear pattern, to that data. So I would say that that is weak in terms of strength, Could I fit a line to that? Well, yeah, we could fit a line to that. We could put a line through here and say that, we have a line that estimates this data. Now, when we get to section 5.2, we'll talk about, is that a good line? Is that a line that we should be happy with? And we'll look at some statistical analysis that will allow us to decide that. But we could certainly fit a line across that data in scatterplot C. Scatterplot D, again, parabolic. If we take a look at this, it's not as strong as this parabola in terms of the grouping of the data around the trend. Here we have a loosely grouped set of data points, but it is certainly, I wouldn't say weak, such as C. I would say it's moderate. If I'm only allowed to choose between weak, moderate, and strong, then I'm going to go with moderate. Should I fit a linear model to this? No, this is absolutely not applicable to a linear model. E, here we have a very strong relationship, right? The strength of the relationship is very strong. This data is tightly grouped and shows a clear linear pattern. So I would describe that as strong and say I could certainly model that data with a line. Finally, in F, it's scattered. It's not as scattered as much as C, but it's still scattered. It doesn't appear to show any kind of a curve or a non-linear behavior that we can see with the naked eye. So I would say it's weak, stronger than this, but weak, certainly way weaker than this. And I would describe that as something that I could fit a line to. Again, I would have to wait until I got to section 5.2 and did my analysis to see if the line was a good idea. Okay, so those are the kinds of descriptions we expect you to utilize when discussing the strength of a relationship and the direction of a relationship and the form, right? Those are our words. Remember, when we're talking about a scatter plot, we want to talk about strength, form, and direction. Right? Those are the words that we use to describe scatter plots. So that takes care of question 3. The next question I'm going to work on is question 6, which also appears in this later version of the book. It appears in the later version as 8.6, but in our book it's 5.6. And this problem is called Husbands and Wives Part 1. It says, the Great Britain Office of Population Census and Surveys once collected data on a random sample of 170 married couples in Britain, recording their age in years and their heights. Here, the heights are converted to inches because we're in America. Originally, they were probably in centimeters. Of the husbands and wives. The scatter plot on the left scatter plot shows wife's age here, husband's age across the bottom. And the plot on the right shows the wife's height and the husband's height. All right. Now, we're not talking in terms of one of these variables being explanatory and one of these variables being a response. We're not saying one predicts the other. We're not saying the wife's height predicts the husband's height. We're not saying the husband's height predicts the wife's height. Okay. We're not saying that about age, that the husband's age predicts the wife's age, or vice versa. We're simply talking about, given these two scatter plots, talk to me about the direction, the form, and the strength of the relationship. So part A says, describe the relationship between husband's ages, which is down here, wife's ages, which is over here. And if we take a look at that scatter plot, we can see that that scatter plot is tightly grouped, right? I would say the strength of the relationship, right? The strength is strong. I would say that's a strong, for form, I would say linear, right? It appears to be a strong, linear form. In terms of the direction, it appears that as the husband's age increases, right, it starts at 20 down here and goes to 60 here. As the husband's age increases, the wife's age also increases, right? So it would appear that as the husband's age increases, the wife's age increases. So describe the relationship between the husband's and wife's ages. That's how I would describe it. I would say, well, that scatter plot demonstrates a strong linear relationship between the husband's age and the wife's age. And I would say there's a positive association, i.e., we always want to put it in context, i.e., as the husband's age increases, the wife's age also appears to increase. Part B says, describe the relationship between husbands and wives' heights. Now that's this scatter plot. In this scatter plot, we can see a weaker relationship than we observed in the one to the left. This scatter plot certainly does not show as strong of a relationship The strength is definitely weaker. It would be difficult to describe this as a strong relationship. We have points everywhere. There does appear to be a trend, though, right? If we look at this, it does appear, the data does appear to go up to the right. So while I wouldn't say it's a strong linear relationship, I would say it's a weak linear relationship. And the direction is it has a positive association. It appears, if we look at the data, the maximum height here in inches is 75 inches. We do not have a 75-inch husband married to a 55-inch wife, right? If we look at that, the super tall husband is generally married to a taller, out of the range of heights of the wives. The taller husbands generally are married to the taller wives. Now, when we get down here on the other end, however, some of the shorter husbands are married to taller wives. Hence the reason we would classify this as a weak, right? A weak relationship. Part C says, which plot shows a stronger correlation, right? A stronger correlation. Now, remember, the definition of correlation is a numerical calculation, right? It's a statistic that gives us the strength of the linear relationship between two variables. That's correlation. The strength of the linear relationship between two variables. Well, the relationship between husband's age and wife's age is much stronger than the relationship between husband's height and wife's height. So I would say that which plot shows a stronger correlation? The one on the left, the one between husband's age and wife's age. Why would I say that? Well, the pattern of the data, right? The data is more tightly grouped around a linear pattern, and correlation measures the strength, the conformity of our data to a line, and that side versus this side has a much higher correlation. That's part C. Part D says data on heights were originally collected in centimeters. Well, there you go. And then converted to inches. Does this conversion affect the correlation between husbands and wives' heights? So originally these two heights were collected in centimeters, but for our purposes in our book, since it's in America, they converted these into inches. Now the question is, because we converted this from centimeters to inches, right? 2.54 inches per centimeter or 2.54 centimeters per inch, something like that. I mean, I don't know. Jimmy Carter tried to teach me that back in 1972, but I didn't learn it very well. So the question is, if we change the units, does that change the correlation? And the answer is no. One of our facts about correlation is correlation doesn't have units. There is no units. Correlation is just a number. So if we change the units, that is not going to alter the correlation. Whether we measure in inches or centimeters or feet, it's not going to be any different in terms of the correlation. All right, so the answer to D is no, that wouldn't change the correlation at all. So that finishes problem 6. The next problem I'm going to work on is problem 12. Okay. Again, it's in this newer version of the book as 8.12, but in our book it's 5.12. And it's called Crawling Babies Part 1. And it says, a study conducted at the University of Denver investigated whether babies take longer to learn to crawl in cold months when they are often bundled in clothing that restrict their movement than in warmer months. That's an interesting question. Infants born during the study year were split into 12 groups, one for each birth month. We consider the average crawling age of babies in each group against the average temperature when the babies are 6 months old, which is generally the age when babies begin to crawl. Temperature is measured in degrees and age is measured in weeks. So we have temperature down below. we have age on the y-axis, and we have 12 data points, one data point for each month. So here we have 30, 40, 50, 60, 70. We can assume the temperatures down here on the right-hand side, those are probably for summer months, assuming this is in the northern hemisphere, where summer is the warmer of the two seasons versus the southern hemisphere, where winter is the warmer of the two seasons. But we're going to assume, since it was done at the University of Denver, we're going to assume these babies are from the northern hemisphere. So these are the warmer months here, and we'll assume that's the summer. These are the colder months here. We'll assume that's the winter. And we're wondering, what's the average age that babies learn to crawl, right? So if we look over here, we have this one point that doesn't seem to fit the pattern at all. We'll come back to that point. So here, we have temperatures in the upper 60s to low 70s, and these babies are learning to crawl in less than 31 weeks. Whereas down here, we have temperatures in between 30 and 40 for these 5 data points here. And all of these babies are learning how to crawl in longer than 31 weeks. Now, with the moderate temperatures, we seem to have some variation, don't we? Here we have a temperature in the low 50s. These babies in this month learn to crawl in like 28 weeks, the low 29. That's quicker than the warm months. But right up here, we have, 48 degrees, 47 degrees. It took these babies over 33 weeks to learn to crawl. So there seems to be some variation with our moderately temperate months, right? Our spring and our fall months. So let's take a look at the questions, right? We've looked at the scatter plot. We've had some thoughts. We've pondered, we've made some hypotheses, we've thought about the scatter plot. Let's see what they're going to ask us. Describe the relationship between temperature and crawling age. Well, if we had to describe the relationship based on these 12 data points, it does appear that in the colder months, it took longer to crawl, and in the warmer months, it took less time to learn to crawl. I wouldn't say this is a strong relationship due to the variation in our temperate months, but we have, a weak, maybe we could say barely moderate linear relationship that shows a general trend for faster crawling times in warmer months, slower crawling times in colder months. How would the relationship change if temperature were measured in degrees and age was measured in months? Remember, age is measured in weeks, temperature is measured in Fahrenheit. What would happen if we changed it to Celsius, and instead of doing weeks, we did days? Months. Nothing. Wouldn't change a thing, right? When we change units, nothing changes. That's what they're trying to get us to realize. They asked us about that in question 6. Now they're asking us that in question 12, right? That's not going to change anything. The correlation between temperature in Fahrenheit and age in weeks was negative 0.7. So they actually calculated the correlation here using RStudio or some other software. They calculated the correlation and they came up with negative 0.7. If we converted the temperature to Celsius and age to months, what would the correlation be? Negative 0.7. All right, we said that in class. We saw that in the reading. When we change units, correlation does not change. So just because the units went from Fahrenheit to Celsius and the age went from being measured in weeks to being measured in months, that doesn't change the correlations. They're going to be negative 0.70. Okay, so these questions are just reinforcing the facts that we've been asked to master regarding correlation. All right, I hope this helped, and I hope you can finish the rest of your homework with this assistance.